Morning everyone. Now we just start our physics class. Now we are going to start our physics class. So in this class we just go for the revision of the topics what we have completed in the last previous classes. We have started with the chapter 1, that is crystallography, and in that crystallography, first of all we need to understand first classification of matter, right? We have discussed in detail about the different classification of matter. So you already know the matter is composed of three divisions: gases, liquids, and solids. So when we just classify the solids, so the solids have been uh, again classified as amorphous, Cossiel crystals, and these crystals are again polycrystals and single crystal. They are again classified as polycrystals and single crystals. So this is the uh, brief, what you can say, classification of matter. So now we just have a different classification of our solids, that is crystalline solids. What is actually the basic difference between the crystalline solids and the amorphous solid? So in the previous classes we had very detailed explanation regarding this. So now in this particular class we'll just go for some differences of the crystalline solids and the amorphous solids. So when we talk, before just going for differences, what is solid? Everybody is having an idea. The solid is nothing but the material in which the atoms are closely packed, right? So we'll just call such material as the solid. So again, the solids have been classified depending upon the arrangement of the atoms and their orientation. They have been classified into crystalline solids and the amorphous solids. So we'll just have a glance of the differences between crystalline solids and the amorphous solids. So the regular arrangement of the atoms in three dimension, so we'll just call such a regular arrangement as the crystalline solids. And when we go for the case of amorphous solid, then you don't find that the regular arrangement or sequential arrangement of the atoms. And the crystalline solids will be considered to be the long range order. So that will come under the category of long range order, and the amorphous solid come under the category of short range order. Now in the crystalline solids you will get a very sharp we have a sharp melting point, and in the amorphous solid you don't find any sharp melting point. So the heat of fusion is very high in the case of crystalline solid, and we don't find any heat of fusion in the case of amorphous solid. So they are called anisotropic in nature, crystalline solid, and they are isotropic. So what is this isotropic, right? So isotropic and anisotropic. So isotropic is nothing but the elements which will have the property same, right, identical property in all the direction. We just call such nature as the isotropic nature. And anisotropic nature is again the opposite of the isotropic. So they have the characteristic, crystalline solids have the characteristic of solid, and amorphous doesn't show the character of solid, but it will come under the solid. And the what you can say, there are different again differences are there. So if you can learn out of this 6 to 7 differences are there, if it is possible you can just have 4 to 5 differences. So this is the classification what has been done in the case of crystalline solids and the amorphous solid, right? So if see here, so we have already learned in the previous classes the crystalline solid detail understanding of crystalline solids and the amorphous solid with the examples, right? So in this particular class we just go for the whatever we have done previously. So we are just going for a very brief understanding of crystalline solids and the amorphous solid. So you already students, some students have a problem in the understanding this starting classes. So that is the reason that again I'm going for this session, right? So now we go for the next slide. When you go to the next slide, you can just see just now we had the differences, right? So regular arrangement, when I say crystalline solids, so regular arrangement of the atoms in the tri-dimensionally. So that should be indicated with some figure, right? Graphical representation or figure, a geometrical figure. When you see the geometrical figure, you'll find that the arrangement points or the atoms or imaginary points are nothing but single crystal. You can just see this particular figure which indicates here single crystal, how these atoms or the lattice points, whatever we are assuming, so it may be in this particular fashion, the ideal manner. Sorry. So now in the case of polycrystalline, you can just see there is some boundary here, right? This is the orientation of this particular arrangement of points is different, and this particular point is very much different, and this is completely different. You'll find this will just the division of this orientation of the atoms will be considered to be grain boundaries, right? The semantic view of the polycrystalline solid. When you see the non-crystalline solid or amorphous, just now we have just gone for the amorphous. So the amorphous, how the arrangement of the imaginary points, lattice points are nothing but atoms. So this may be the ideal case of arrangement of the points, right? So when you see it in a microscopical view, you'll find that the polycrystalline look like this, right? You can just see the grain boundaries. We'll call this are nothing but they are called grain boundaries, right? Now this is information is very important. See how we can classify it geometrically. So that is the reason that we are just studying about this single crystal, polycrystal, and non-crystalline solid. So two-dimensional representation of single polycrystalline and the amorphous materials. So you can just have a glance of it. So I think that you got some idea regarding the classification of the solids. That is particularly we talk about the single crystal, polycrystal, and the non-crystalline solid or amorphous solid. So the geometrical view and also the microscopical view in two dimension. We are talking about two dimension, right? So actually this exists in three dimension, but our naked eye cannot see the three dimension figure. So therefore we need some separate lenses for it. So now what we can do is that we just first of all we'll just imagine the geometrically the arrangement of the points in this particular manner. So two dimension representation of the single polycrystalline and the amorphous material, you can just see it right now. So before going for this, see in the previous slides we just have a look into this arrangement of the atoms. So now in order to study it more in more detail, so what we are doing here is that we are just taking the help of some important parameters, right? So directly I cannot see the atom. You know that we cannot see the atom. So we need to understand some important points here, parameters to in order to know the exact the property of the different crystals. So what we are doing here is that first of all we are going for some imagination, and that imagination will lead us to the geometrical view of the structure of the crystal, right? So now that what we are doing here is that we just go for the different lattice form. So what is actually see for imagination, starting from the imagination part. So we are just geometrically imagining that how the lattice look like. So what is lattice actually? An infinite array of points, and each point will have the same identical surroundings. You can just see that has been shown by this particular figure. You can just see this is one dimension arrangement, imaginary array of imaginary points, and the distance between them are identical. That is nothing but you will just writing it as a magnitude of a. And see why we are getting each point will have same identical surrounding. This point and this point and this point is with respect to any of the neighboring atom will have the identical surroundings. So now we'll just go for the plane lattice. So this is called linear lattice. First figure come under the category of linear lattice, and here the arrangement is plane lattice. And here when we go for a three-dimensional figure, so that will be in this particular fashion. Your structure of the unit cell, a combination of regular arrangement of the unit cell will give us the this is the imagination what we have done for see linear lattice one dimension. This is two dimension and three dimensional view. See lattice we can assume in one dimension, two dimension. See you can just two dimension, right? This is two dimension, x axis, y axis. Here you'll find three dimension, x axis. Here you find x axis, y axis, and z axis, right? So this is the linear lattice, plane lattice, and space lattice. So now first of all, see why we are going for translation vector only. Why I am not going for any other vector here? Why? Because translation vector, see we just discuss each point will have identical surrounding. So the translation function, we know the definition of translation function is that we are repeating the same point infinite number of times. If you repeat it, so we'll get a translation vector. So for that instant what we are doing here is that we are origin is there. Here you find that there is an origin here. So we are just taking it as a reference point here. So these reference point is considered to be what you can say, I'm joining this imaginary points with a line segment. You can just see. Let us consider this x-axis and y-axis and get a what you can say. This is O A and this is for your OB, and the distance between them is B bar and so on. And this distance, see, this is A and the A and this is A. The total distance is come to be 2A. So this OB is the resultant vector. So therefore, we are writing OB bar is equal to 2A bar plus B bar. Now this is the geometrical nature of the lattice point, arrangement of the lattice point mathematically, how we can write it down by seeing the schematic graphical representation. Now we have already learned that what is actually the meaning of basis. So basis are nothing but the constituent particles which are present in the solid, either it may be atoms, ions or molecules, which are having each lattice point which is producing means what we are doing is that these, if you arrange the lattice point, you can just see what is this actually I'm talking about. These are the lattice points, imaginary points. If I associate instead of these lattice point, I'm associating, you can just see the black and the red sphere. So if I'm associating this imaginary point with atoms or molecules or the ions, then whatever the pattern you'll observe, that pattern is nothing but we'll call such pattern as crystal structure. See, if I remove this atoms or molecules, right, I will just call that structure here. See here, imaginary point is associated with one of the atoms or molecules or the ions. So we'll call such thing as the basis. If you join this basis with the lattice points, so whatever the pattern you'll observe, that pattern is nothing but crystal structure. So now that is the assumption what we have made in the previous classes, and also here to understand the exact arrangement of the atoms. Now what is the figure that we'll get two-dimensionally or three-dimensionally with respect to this imaginary point? So what type of figure will obtain, you can just see here. So the important building block of the crystal, see in the previous class also, some classes I have taken the example of construction. If you want to do some construction, you have to use some huge number of bricks. So if you join that bricks, you'll get a particular structure. Here also, if you join the unit cell, if you join different infinite number of unit cell, whatever the structure you'll obtain, that structure is considered to be the crystal structure, right? We'll get a building structure. You just we'll take an example of the construction of your construction of the house, any house. So if you construct the house with respect to how we'll construct the house, we'll take the help of bricks and other parameters and other materials. But if you just infinite number of times, if you just let us consider, so we are just using some finite or infinite what you can say bricks. So whatever the structure you'll obtain, that structure will be considered to be your building structure. Here in the same manner, if the unit cell number of unit cell whatever you are seeing by means of this schematic diagram, if we build up that particular unit cell in infinite number of times, so whatever the structure you'll obtain, that structure is nothing but we'll call such as crystal structure. So actually we just start with the basic entity. The basic entity says that if you just join these points here, we are joining the points here, you can just see it is a building. Unit cell is nothing but a smallest geometrical figure. On translation repetition, it will give us the exact structure of the unit cell. So there are different types of unit cell. You'll find that what are the unit cell you'll find, you will get a primitive unit cell and non-primitive unit cell. What is the actually meaning of why we are going for primitive unit cell or non-primitive unit cell? See, when you see the geometrical figure, you can just see the geometrical figure here. So when you see the geometrical figure, so whatever the figure you'll obtain here, so at the end we will just consider the first figure. In the first figure, if I join any 4 points here, two dimensionally, I'm talking about two dimension. So I'm talking about two dimension. When I join this any 4 points, right? So these 4 points, when you join it, so this particular cell is nothing but we'll call this as a primitive unit cell. Now non-primitive unit cell, what is the meaning of non-primitive cell? You will find that imaginary points are at the only corners. Now here you will find that the imaginary points are not only at the corners, but exactly it is residing at the center of the point. You will find one more unit cell. So that unit cell, one more imaginary point other than the corners. So you find that particular structure is considered to be that unit cell is considered to be non-primitive unit cell. Now unit cell, you again see again unit cell. I now to have very detailed understanding of that primitive we have given. See, this is two-dimensional unit cell and this is three-dimensional unit cell. If this is the case, you can just see, this is the case, I will call such as primitive. Primitive is very small. What is the meaning of primitive? It is very small. Non-primitive, why we are calling non-primitive? So other than the corners, you will find two, I'm talking about two dimension now here. So here, if it is two dimension, you will find that the apart from the corner, you'll find that one more lattice point here. So that particular unit cell is considered to be non-primitive unit cell. Now we'll go for the now we'll understand the unit cell more clearly by considering the what you can say the lattice what is lattice parameters and crystallographic axes. We'll just have a glance of it. Let us consider a unit cell. Now you know that we are talking about three dimension. Till now we just go for two dimension. Here we just go for three dimension. This is three dimensional unit cell. When you go for three dimensional unit cell, see x axis, y axis and z axis. The axis chosen here is nothing but these axes are nothing but you can just write it down. See, this is geometrical assumption. You can write here x, y and z, right? There is need not be necessary that I have to write here itself, right? So x axis, y axis and z axis. So here the angle which is formed throughout the x axis is nothing but alpha, and here the axis the angle which has been formed is beta, and from here the whatever the angle you'll find that is called gamma. So here the axis resulted by intersection of three non-coplanar faces. We have just chosen three non-coplanar faces which are not equal to each other. See the three lines, right, which are passing from the three different faces. So what we'll say suggest that these axes are result by the intersection of three non-coplanar faces of the unit cell. So the angles between these faces are considered to be the interfacial angles or interaxial angles. So now if I just take the interfacial angles and the combination of these what you can say translation vectors ABC are nothing but translation vectors that gives us the dimensions of on the x-axis, on the y-axis and on the z-axis. See, if I write say from this is the origin and this is considered to be some A, that is a vector represented by the vector A, translation vector A, B and C. So what you will call such particular vectors are nothing but translation vectors are primitive ABC of a unit cell. So along x, y, z axis and interaxial angles alpha, beta and gamma. So now this is the case if I just join this ABC and alpha, beta, gamma. So whatever we are getting that particular values, we'll just call these parameters, right? So these parameters are nothing but we'll call such parameters as lattice parameters. I think that you got a clear idea regarding this lattice parameter. So why we are studying about this lattice parameter? By building these lattice parameter, one can know that so if the exact structure of the or system of the crystal. So on the earth crust you'll find that there are 7 crystal systems. So how you can know geometrically the particular solid is belonging to which type of crystal system. So by means of these lattice parameter we can easily understand that this particular if the condition of if ABC, the relationship between ABC alpha beta gamma, the relationship, by seeing that relationship you can say that the particular system crystal system belongs to the either it belongs to cubic or tetragonal. That is a name which is given to the different crystal system. Now in the next slide you will understand what I am trying to tell. So if this is the case here, if A is equal to B is equal to C and alpha is equal to beta is equal to gamma is equal to 90 degrees, then if this structure is known as, this system is known as cubic crystal system. So this also we have just gone for the very in detail. We got this particular aspect in the previous classes. We had a detailed explanation of this. Now this is in the same manner, if this is the case, if these lattice what you can say constants, if they are satisfying this condition, so then we'll call such crystal system as tetragonal crystal system. And if this is the case, we'll call such thing as such system as orthorhombic crystal system and monoclinic crystal system. You can just see if this condition is satisfying, then we can say that the given system is belongs to which category, that is monoclinic crystal system, and if everything is not equal, every lattice parameter is not equal, this is the a special case in the 7 crystal system. If this is the case, we'll call, if this is condition is satisfying, we'll call such crystal system as triclinic crystal system. And also the trigonal crystal system, you can just see that the given entities, lattice parameters, if this is the case, then you can we can call such crystal system is as this is comes under the category of rhombohedral, or we'll call such system as trigonal. Now hexagonal, if this is the case, see A is equal to B, B not equal to C, and alpha beta is equal to 90 degrees and gamma is equal to 120 degrees. If this condition is satisfying, we can say that this belongs to the hexagonal system. So likewise, on the surface of the earth, you'll find 7 crystal system, and how to identify that 7 crystal system geometrically, so that, and with the help of some entities that is called lattice parameters, we can know the exact form and size. What is the use of studying lattice parameter and the, so lattice parameters are used to study, to know the exact size and the form of the given what you can say, the crystal systems. So now this is this whatever we have just summarized into a given table here. I have just summarized it to given table here. So how this crystal system, will call that as interfacial interaxial angles or interfacial angles. So the lattice constant relationship I have shown you, and the unit cell geometry, how the unit cell look like. So we have taken on the first side crystal system and the lattice parameters. The lattice parameters is nothing but the combination sum of the axial relationships and what is axial relationships here? Axial relationship is nothing but the dimensions with respect to the crystallographic axes, that is x-axis, y-axis, and z-axis. When you see the interaxial angles, you'll find that if this is alpha, beta, gamma are nothing but we'll call that as interaxial angles or interfacial angles. If this condition is satisfying, we just call such thing as the crystal system is nothing but it is cubic crystal system, and so on. Just now we had discussed this particular thing. So now in the second session, we had studied about the Bravais lattices. So in the each system, you'll find that what we have just studied in the previous slides, that lattice is nothing but it is the nothing but it is having identical surrounding. So how identical surroundings can be arranged? So Bravais is a scientist who has given us the information that in 3 dimension, in 2 dimension, 5 different ways we can have the what you can say, we can just arrange that lattice points such that each lattice points is having will have the same surrounding. We are talking about geometric what you can say, geometrically the arrangement of the points. So now in Bravais says that there are 14 different ways by which we can arrange the lattice points, right, of 7 crystal system. So how they have been obtained? By combination of, we'll call that as crystal system or lattice system with the lattice types. So lattice system, see again it's a lattice system. If I take about lattice, I'm talking about lattice, that is nothing but I'm talking about crystals. So crystal system gives us the given information regarding the lattice parameter. So what are the different types, lattice types, given information about lattice point present in the given unit cell? So this is the different lattices. So 4 lattice points are present, and that 4 lattice points have been divided into 7 crystal system. If you join that particular, if you sum up, so you'll get each crystal system, some crystal system will have 3 lattice points, right? Primitive, we just see here, primitive means very small, so that is if the lattice points are arranged at the corners, we'll just call it as primitive. Body centered, exactly at the center, you'll find apart from the corners, one more lattice point or the atoms are situated, and in the face center, you'll find 3 points, right? It is like a coin, right? So sir, it is, see when when I see this particular figure, I will get how many points I'm seeing? 1, 2, 3, 4, 5, and 6. So how it is possible, sir? How you are telling 3? So 3 means it is like a coin, right? So one coin is having head and tails. 2 sides will be there. So head will be shared by one of the face. See, like this, head is shared by this face, and the tail portion is shared by this face. So how many faces? One coin or one lattice point is shared by 2 faces. So how many faces the cubic unit cell is having? 6 faces. So how many lattice points or atoms are there? 3. So 3 apart from the corners, you can just see 8 into 1 by 8 plus 6 faces, and each face is sharing half part of the what you can say the lattice point or the atom. So the what is the n here, n indicates what, the number of atoms per unit cell. We just see, we talk about unit cell here, these are nothing but unit cells. So unit cells, so how many number of atoms are there in the unit cell? Here if I talk about face centered, it is 4, and base centered you have only 2. So that is directly we are just writing it as 2 here. So 2 into 1 by 2, that will give us the 1, and from here you will get 1. So that is nothing but 2. So this is about the primitive, body centered, face centered, and the base centered lattice types. These four lattice types are arranged here in the say case. Now this is we don't require this particular aspect. Now we move to the next important parameter, that is nothing but what you can say here is that uh, the Bravais lattices. When you talk about Bravais lattices, see, Bravais lattices. Just now we just had the information regarding the Bravais lattices. Now we are going for the different lattice planes. So see, when I talk about lattice points, you are only joining the points. So let us consider this three points I'm joining in this particular fashion, right? This is the vertical type of line segment. So this is nothing but we'll call this as plane, right? Now this is one type of plane, this is another type of plane, and this is another type of plane, and these two planes are separated by equidistance here. So equidistance is nothing but a small d. So equidistance is nothing but a small d, right? So this is I'm talking about this particular thing is nothing but we'll call this as lattice plane. Why lattice plane? These points have been joined, lattice points have been joined. So whatever the structure you'll obtain, that are considered to be lattice plane, right? I think that you got some idea regarding the lattice planes. Now see, and these lattice points, why we are studying about these lattice planes? Why? Because see, in the solid you'll find that there are a number of close arrangement of atoms. So where we want to find out where actually the more concentration of atoms is situated. So that in order to find out that particular aspect mathematically, the scientist known as Miller has given us the information that if you find this Miller indices, he has given information regarding the crystal planes, right? Mathematically, how you can find out the exact values of the crystal planes of different crystal lattices. So here, now you can say that how you can find out the Miller indices. This is the mathematical, what you can say, the values which has been in Miller indices is nothing but which give us the smallest possible integer, the information regarding the crystal planes in the form of a smallest possible integer mathematically. So how we can locate this Miller indices? So there is a procedure. Miller says that I'm giving you the procedure to find out the actually the Miller indices, and from that Miller indices you can know the exact where the more concentration of atoms are there mathematically. So now in order to know this Miller indices procedure, he has given us some important parameters and points to determine the Miller indices. So here what we are doing is that we are actually determining, first of all, what is the condition. He has given procedure. See, procedure to find out the Miller indices. So first case, in the determine the coordinates of the intercepts made by these planes. Here in the previous slides, this I'm talking about these planes, right? So he says that determine the coordinates of the intercepts made by the plane along the three crystallographic axes. When I say plane, see, when I say plane, so when I talk about plane, so plane is nothing but x-axis, y-axis, and z-axis. So he says that what is the intercept on the particular axis, x-axis or y-axis, 1 or 2 or 0, whatever it may be. You just first locate the intercept of the along the coordinate axes, that is called crystallographic axes, and express that intercept in the form of you can say that the intercept is nothing but just locate that intercept along the crystallographic axes, and then whatever the value you'll get, that should be what you can say divided, so that reciprocal of it will give us some number, fraction value. So now reduce this reciprocal into smallest integer or the whole number. So multiplying, so how you can reduce it? By doing the LCM, right, to get the smallest whole number, right, and enclose this whole number into a bracket, and this this will give us, see, whatever the value now we'll get, that value is nothing but HKL in the form of HKL. That is not comma. If I write comma, then it will consider to be not Miller indices, but it will come considered to be a point. So we are not talking about a single point on the plane. We are talking about the plane. So when you talk about a plane, so you don't consider it to be a point. So that is the reason that it has not been marked with some commas here. So this gives the Miller indices. This is the procedure by which we can find out the Miller indices. And Miller indices has given us some what you can steps to move forward. It is like a game, right? So if you want to play a game, so you need to understand the rules and regulation of the game. So this is the rules by which we can know the Miller indices. So that is the reason that we have shown you in the last classes also. I have been showing you I have shown you the plane. So if this is the plane, you again see this is that is the reason that we have indicated with the colors. Right? You can get different color here, right? So this is the plane, and this plane is nothing but, see here, A is along the A is the intercept along the x-axis, B is the intercept along the y-axis, and C is the intercept along the z-axis. You can just see this plane is not intersecting on any point on the z-axis, but you can just see that this plane is parallel to z-axis. How it is possible, sir? You can just see this is a vertical line here of a plane. You just see this is a vertical line, and this particular line is parallel to z-axis. You can just see here. So if it is, if any you see, if the plane is parallel to any axis, then it should be taken as infinity. From the origin, what will be the smallest distance? 1 unit. So that is the reason that we have taken one A as 1, and from here to here the smallest distance is unit. So therefore we have taken it as B. And C, since it is not exactly coinciding or intersecting, just we have taken it as an infinity. So 1 by 1, 1 by 1, and 1 by infinity. You already know 1 by infinity is nothing but 0. So 1, 1, 0. So reduce it. If you take a reciprocal also, you have taken the reciprocal, and 1, 1, 0, 1, 1, 0. So Miller indices is 1, 1, 0. Now this is the case for see, this is the procedure you have to follow for each and every what you can say to locate the Miller indices of the given crystallographic planes. So now this example 1, I think that you got some idea regarding the crystallographic planes and how to locate the Miller indices. Now this is the third example, right? You can just see this is the third example we have already discussed, but since it is a revision class, I've taken one example. So you can just have a pause of this particular video. So then you can just locate it, and you can just write it down, and then what you can do is that you you can just understand it more clearly, right? So when the once the class has been completed, and whatever the doubts you will be having, so definitely we are here to help you out regarding the clarification of doubts. So now this is the how this geometrical what you can plane, and what is the important things that we need to remember. See, while what finding out the Miller indices, what is the things that are be very important. So if see just now we just consider if a plane is parallel to any of the coordinate, just now I told you in the example 1. So if a plane is parallel to any of the coordinate axis, then the intercept will be infinity, and all the parallel equidistant plane have the same Miller indices. So Miller indices define a set of equidistant parallel planes. Miller indices define a set of equidistant. Just now we have crystal planes. Equidistant, you can just see the this. I'm talking about the C. I'm just talking about this, right? Equidistance. You can just see this. This is called equidistance planes, right? So he talks the same. See, Miller indices define a set of equidistance parallel planes. So if the Miller indices of two planes have the same ratio, then the planes are parallel to each other. For example, we just considered 2, 2, 2, and that 2, 2, 2 is nothing but 1, 1, 1, right? Can be right as simple as if HKL are the Miller indices of a plane, then the plane cuts the axis into HKL and into equal parts. So now this is the case for the what you can say the now see I just now again I'm going to the previous slides. Why? Because what is actually this D? See, we just we written read a small d, that distance between, this is called equidistant plane. So what is this? Is D is known as interplanar spacing. So in the previous classes we have shown you the detailed understanding of the derivation of the interplanar spacing. So that interplanar spacing come to be for cubic crystal. You can just see that particular video, right? I think that is a class number 6. In the class number 6, you can class number 6 or 7, 7, it seems 7, right? So you can just see that class 6 and 7, you will understand how we got these values, right? 1 by d square is equal to h square k square plus l square by a square. Now this is how the cubic crystal system, this is what this is indicating, that the mathematically the d value, if you want to know the interplanar spacing for the cubic crystal system, you have to use this particular formula. For tetragonal system, you have to use it, and for the orthorhombic system, you have to use it. So interplanar spacing in the other crystal system is more complex. Other than, see why it is written like this? Why? Because the we are for these three crystal system, it is okay, right? You can have this particular mathematical expression. If we already told you that there are 7 crystal system, so for other crystal system, what will the interplanar spacing? It is a bit complex, so you need not to worry about that interplanar spacing derivation. Now for our syllabus is concerned, so we just concentrate on this cubic, tetragonal and orthorhombic, and particularly we are trying to concentrate more on cubic crystal system interplanar spacing. So now this is the end of this session 2, that is the second part of our syllabus, and you find that you can just have an different formulas of numericals. You can just see the question number 1 within a cubic unit cell. Now you have to sketch it by seeing the Miller indices. You have to sketch the what you can say planes now. So how, sir, how it is possible? You can just see this figure, right, in the previous cases, right? 0 0 1, you have to see, this is a sketch of the plane 0 1 0 1 0 1. You can just turn the slides, you can easily understand what actually I'm talking about, right? These are the crystal planes. So Miller indices is given, you have to sketch it. You have to draw that particular figure, right? So now determine the Miller index of the plane. Now again, this is given to you, you have to determine. This is completely reverse, right? So this is the way that the numericals will come in the examination. So please try to do this as an homework and an assignment. So such that if you have any problem, again this particular part will be again repeated to you, right? So now, and the next session we have just gone for the diffraction through crystal, and I think that I have gone very it is very clear to you regarding the diffraction of the crystal. So that is the end of the session 2. No, right, and we are here, right? So diffraction, in the diffraction case, we just discussed about the diffraction of the, what is actually the meaning of diffraction. So I think that everybody is having the idea of diffraction. So what is actually the meaning of diffraction? It is nothing but it is the bending of the light ray at the end of the what you can say, end faces of the obstacle or the object on which the light radiation is falling. So when the light rays bend, so we'll call such bending nature of the light as diffraction, right? So that bending nature of light diffraction will consider to be what you can say, bending nature of light is considered to be diffraction. So what is the main important condition that the diffraction is taking place? So in order to have a diffraction phenomena, so what is the important condition? That always the obstacle or the object or the slit from which the light ray is passing or hitting the obstacle, so that should be comparable with the incident wavelength of the light. And this particular diffraction in crystal phenomena has been given by the scientist called the Loy, and which has he has suggested a three-dimensional arrangement of the points in the crystal, and which can see there are three-dimensional arrangement of atoms which we already know, and these three-dimensional arrangement of atoms can produce diffraction, That phenomena is given by the scientist, German scientist, that is called Loy. So this is called diffraction in crystal and X-ray diffraction in crystal. What is X-ray diffraction in crystal? See, we just studied about diffraction. So what is the light ray? What is the ray we are taking here? X-ray. Why? Because the atomic, you can just, I will just show you the wavelength of X-ray is the order of angstrom, which is in the range of spacing between the atoms inside the crystal. The spacing between the atoms and the wavelength of X-ray is comparable with each other. That is the reason that we have just using here X-ray. So X-ray diffraction in crystal. So why we are studying about diffraction through crystal is that we need to understand more clearly where actually the what is the structure of the crystal. When you understand the structure, you can know the exact properties of the crystal. When you understand the properties, then you can know that particular material can be used for what purpose, right? So that for purpose, for our comfortableness, we need to understand different properties of the crystal. So for different usage, right, for our convenience purposes, and also for R&D department and the for different daily life applications. So just now for daily life applications and R&D department, first we go for the daily life application. Where actually it is being used, the X-ray diffraction in our daily life, right? So we came across this particular aspect in our daily life also, but we don't know the exact principle behind that. So here we need to understand what is the basic principle of the usage of the X-rays. You can just see this. What is the significance of using the X-rays? So in medical field, how these X-rays are used, right? So you can just see the crystallography you are seeing. You can just see this this by seeing the figure. What you can conclude, this is about the fingerprints. So wherever you find a what you can say any incident happen, now that is forensic team will go and first of all they investigate regarding the fingerprints. So your X-ray photography, X-ray crystallography is being used for first of all the uh, for daily life, what you can say, a very important application, fingerprints, right? And then you can just this thumb and this impression of the medical, right, you can say, and the airport security also, where you will use this particular X-rays, right? So X-rays, soft X-ray, and they are having ranges. You can just see the range. We use the hard X-rays in order to know these hard X-ray, and the range is given here, right? You can just see the range, this range, and this range is coming under the category of hard X-rays, and these type of X-rays we use for our daily life, what you can say, application, in daily life application. That is a very important application of X-ray, where actually we are using. And this is only the single case of a daily life example. You'll have a numerous example for R&D also, in order to know the exact characteristic of each characteristic of the what you can say, the atoms, how the atoms are there. You'll get some different peaks here. I have shown you the video in the last class, what is a diffraction, what is X-ray diffraction, the importance of X-ray diffraction. So here, right, so now here I will just the we know that how these X-rays are being produced. This is the case. Now, what is the Bragg's condition? See, when X-ray diffraction is taking place, if this condition is satisfied, then only the diffraction takes place mathematically. So that has been given by the two scientists. That is Bragg's son and father scientist. That is called W.H. Bragg and his son W.L. Bragg. So that particular instant Bragg's law also we have studied in the previous classes very clearly, and have shown you the video regarding the this particular condition, how we can obtain this condition. If this condition is satisfied, then only we can say that the diffraction is taking place. Now diffraction is taking place by the phenomena called constructive interference, and so on. Now this is a derivation, already it is there in the previous classes. So this is the end of session 3. Now I think that I have covered the entire aspect of the topics which has been taught to in the last classes. Different problems, numericals will definitely will come to you. So what is the different methods that will apply for X-ray diffraction? Here there are 3 methods, but we are just going for the one method only, powder method. So in the powder method, what is the thing that we have discussed in the previous classes? Very fine polycrystalline material we are taking, and we are taking a monochromatic X-ray, and the scientist camera, the DB Shearer camera we are using in order to know the properties of the crystal. Now this is the thing that we have discussed in the previous classes, how we'll obtain the, by means of negative film, we can obtain these types of cones, right? So now obtaining these cones, what are the applications? You can determine the different lattice parameter of the, see what sir, why we are studying about lattice parameter here? See, if the crystal pieces are in a powder form, we want to know that powder form belong to which cubic crystal system. So now by means of this powder method, you can know that lattice parameter. Once you know the lattice parameter, you can just say, tell that you know the lattice parameters are A, B, C, and alpha, beta, gamma. You can know that lattice parameter. If you know that condition, then we can say that the particular crystal will come under the category of the which crystal system, either it is a cubic or tetragonal, and so on. Now there are different applications of this X-ray diffraction technique. So you can know that given crystal is a crystalline, given what you can say, if crystal is given to you, by means of this X-ray diffraction, you can come to know either it belongs to crystalline solid or amorphous solid, or the structure, determine the structure of the exact crystal materials, and also how these electrons are distributed within the atoms of the unit cell, and also how the orientation of their single crystal, polycrystal, and you can measure the grain size. And this, see here, what is the thing, you see where is the, what is it, orientation, texture, strain, and small grain size. This come under the R&D department, and which will definitely in the coming classes you will come to know that where actually this orientation, texture, strain, and small grain size are actually useful. Now this is the more applications, and which is been now also, and in the future also it is of a primary importance of regarding this. Now advantages, you can just see the different advantages of using the X-ray. Why only X-ray? Why not the other X-ray? So these are the advantages, and this is the only one disadvantage. You will find that why actually we are going for X-ray diffraction. And in the X-ray diffraction, we are using the what you can say, the method that we are going for, that is the method of powder method. Now different see numericals are there. See the last class we'll just go for that numericals. I think that we had a very clear idea regarding this. So with this we'll just come to the end of today's class, right? Thank you everyone for listening patiently. So now you will have from today, I will add my number to your group, right? So still you can directly contact me by message, right? So if someone is not exactly following the class, you can just please message me such that I can have I will go very slow, or I will apply some different teaching methodologies to make you understand, right? Thank you everyone. Thank you for your patience.